Okay, ladies and gentlemen, let's do a little bit more integration. We still have more integrals that we can't otherwise integrate using the old power rule methods that we're used to. So the first things first, I want to integrate something that looks like this. If I had an x up top, that would be no problem whatsoever. I'd use a u substitution. If I had an exit now here, again, u substitution, but I don't have those in this case. What I have, though, is I begin to look at and I say, well, wait a minute. Square root of something squared plus or minus something else. That looks vaguely like the Pythagorean theorem. So if I have something that is in this form, I know that I have a triangle with legs A and B. I know that if I were to rearrange this and say have a squared equals c squared minus b squared, square root both sides of that, if I have something in this ballpark, now I have something where I know the hypotenuse and I know one of the legs. Now I don't know necessarily which leg I have, so I can determine the leg that I wish, and that would allow me to find the missing leg, which would be in this case c squared minus b squared. Now, that Pythagorean property allows me to put some things to use. If I were to say cosine of this theta right here, I would say cosine of theta equals adjacent over hypotenuse. I could also say sine of theta. That would equal c squared minus b squared square root all over hypotenuse c. I could also go into tangent, cotangent, so on and so forth, using the sides of the triangle. Because whereas this might be something fairly ugly, this is something that I can readily differentiate or integrate with no problem. Now, the first things first, we need to practice drawing a triangle. And when I say practice drawing the triangle, I mean use the information from the problem to set it up correctly. With this, it looks most like this situation here where I have the c squared first, so x is actually the hypotenuse. That leaves my leg, one of them, to be 3, and the other one to be x squared minus 9. Now, that's how I'd set this one up. But if I go over here, I would set this up a bit differently because it's plus sign, x squared plus 16. I'm going to say I have two legs. Now, I'm going to default and put x on the x-axis just out of habit. So that would make 4 the opposite side. It doesn't matter. I could turn them around just as I had x over here for the hypotenuse. But in the end, I now have all 3 sides. Down here again, I have a hypotenuse, and that hypotenuse seems to be a 5, with one leg being an x, and then therefore I have 25 minus x squared as the other leg. So the setup here is important, because now I look at my problem and I say, okay, how can I replace this mess with something better? Well, what do I have where the opposite side is on the bottom? So opposite side on the bottom, I have sine is opposite over hypotenuse. Tangent is opposite over adjacent. Well, that would be opposite on top. So if I go cotangent of theta equals the square root of x squared minus 9 over 3. Well, excuse me, strike that, reverse it. 3 over square root of x minus 9. Now, that's nice, except that I don't have a 3 up top. But if I put a 3 in up top, I just have to put a 1/3 out front. So I can say 1/3 cotangent theta. Now, that is still using dx. So how do I get rid of dx? Well, to get rid of a dx, I have to know what x is. The easiest thing to set x equal to is to say that hypotenuse over adjacent. Well, let's see here. x over 3, hypotenuse over adjacent would be a secant square, or a secant x, or secant theta. So in this case, I'm going to multiply by 3, and x equals 3 secant theta. And I find dx equals 3 secant theta tangent theta d theta. So now I take my dx and replace it. I have 1/3 integration cotangent theta times 3 secant theta tangent theta d theta. Now what's nice about that is cotangent and tangent cross out. The 3 and the 1/3 cross out, leaving the integration of secant theta d theta. Now, secant theta d theta. At this point, I say, oh, yuck. But I can simply take reference and find the integration of secant theta, and the defined integration for secant x dx is the integration of the not integration, because the integration is the natural log secant x, in our case theta, plus tan theta plus c. Now, that is the integration. The only challenge here is that's still in terms of theta, and we were asked for the integration in terms of x. So I took x, I defined it in terms of a triangle, replaced it with a theta in terms of theta so that I could integrate using theta, and now I have to put it back. But if my triangle is still the following, all I have to do is figure out, well, what is the secant of theta? The secant of theta is the hypotenuse over adjacent. Boom. The tangent of theta is the square root of x squared minus 9 over 3. And now everything is back in terms of x. So using that information, I'm able to, again, use the information to draw a triangle, use a trigonometric substitution based on hypotenuse and legs, integrate the trig function, and then replace the theta back with x.